All right, 4.3, interaction forces. So we'll start by defining interaction pair. An interaction pair is when you have two forces that are in opposite directions and have equal magnitude and act between the same two objects. So these exist together as a pair. They don't exist separately from each other. So they either exist together or not at all. This is also called an action-reaction pair. So basically on one side you have an action, and then in reaction to that you have an opposite force, equal and opposite to the first force. So for example, if you were to push on the wall with a force F, you don't go anywhere because the wall will push back on you with the same exact force. So you have the force of U on the wall, so force Y on W, force of U on the wall, and that's you're applying it to the right. But if you don't go anywhere, there must be an equal opposite force going back on you to keep you in place. And that's the force that the wall exerts on you, which is the force of the wall on you. And we know they're equal and opposite because you're not moving. Now, if you were to punch a hole through the wall, then what's happening there? Well, it's an unbalanced force. Now you're exerting more force on the wall, and you're able to break through the wall and accelerate through it. In a situation like this, where you are not moving and the wall is not moving, we have balanced forces. This is an action-reaction pair, where what you do on the wall is what the wall does on you. And so it's always equal and opposite forces between two objects, in this case, you and the wall. So that's interaction pair. Do you all have this down? Another example would be this. If you were to think about, the gravity pull that Earth has on an object, so if we were to have, say, a table on Earth with a ball on it, so we know that Earth exerts a pull on the ball on the table and keeps it in place. So we can say is this, that we have the force of Earth on the ball pulling the ball downward. What's the reaction to that? So we can think of this a couple of ways. We could say, well, the ball's pulling against the table, right? Is that the action pair, though? Is that the reaction to what the Earth's doing? Remember, we have to have the two same objects, right? So if we're thinking about the force of the Earth and the ball, what's the opposing force to that? Just the reverse, right? Exactly. And so that would be our true action-reaction pair. And so our opposing force, we would say, would be the upward force, like this. And what is that? That's the force of the ball on the earth. Which kind of sounds strange to say, but the ball actually attracts the earth as well. Exactly. So you have the same exact arrow length. So I made this a bit too long right here. So the arrows are always the same exact length. They're always in opposite motions, opposite directions, and they're on the same two objects. So the earth pulls the ball down, but the ball pulls the earth up, or the ball attracts the earth up anyway. The ball can't really pull the earth up, but the ball attracts the earth to it. It definitely does. That's a different action-reaction pair though. So we can think of that too. Let me draw it on this side over here. So one action-reaction pair would be the ball and the earth and the ball. But we can think about just the table itself. I'll just draw it bigger over here so we can see it better. So we can think of just the ball and the table, and we can say, well, the ball is exerting a force downward on the table. So force of ball on table. What's the reaction to that? The ball exerts a force down the table. Exactly. So we have an upward force the table exerts on the ball, force of table on ball. So that would also be an action-reaction pair we could talk about right here. So we have more than one. And usually there are many we can think about, but those are the two main ones to consider in this example. So gravity's like magnetism. We don't think of it that way usually, but it's between any things that have mass. You know, so this tissue box attracts the papers on the table. The book attracts the table. Everything that has mass attracts each other. But we are not aware of it because friction keeps things in place. But there is an attractive force between everything that has mass. And so the ball does attract Earth because of gravity. It doesn't just pull it down. Gravity also attracts things upward to objects above the Earth's surface. Okay, so we can convert between mass and weight as we did yesterday in class. Go through an example of that. If you have a softball, and the mass of the softball is equal to 0.18 kilograms. The question is, what is the force that Earth exerts on the ball? So let's think about this. So Earth pulls the ball downward. So it's above ground right now. We know that there's a force that pulls softball to Earth. So we can say that there's a force of Earth on the softball. So I'll just say E on S. So force of the Earth on the softball pulls the softball towards the Earth. We also have an opposite force, right? We have the force of the softball on the Earth pulling it upward. So we would have an opposing force, the force of the softball on Earth pulling the Earth upward. So the question is, what is the force that Earth exerts on the ball? So we can use Newton's second law where it says force equals m times a. And we can solve for the force if we know the mass and the acceleration. The mass was 0.18 kilograms, what would the acceleration be? Well, there's different kinds of acceleration, right? So if we just say the ball is in our hand, we'd say, well, it's not moving, right? But what is gravitational acceleration? What is gravity's pull on the ball? What would that be? That's right. So we're going to use that. So if we're asking about force of the Earth on objects, that's gravity. We always use 9.8 for acceleration for gravity or for weight. So we are going to use 9.8 for acceleration because that's what gravity accelerates things downward with. .18 times 9.8 gives you the weight of the softball or the force of gravity on the softball. That would equal 1.8 newtons. The last thing is to say the direction. Which way does Earth pull on the softball? That's right. And so we can say to the center of the Earth, we can say downward, because usually that would be how we would see things, is going down to the ground. Or we could just say negative, because generally downward is negative. And so, well, it depends on our perspective. Yes, there is. Now, of course, like somebody in the South Pole, they're like this on the South Pole. So their down looks like this. Somebody in the North Pole, like somebody over here, you know, say where we are, and their down would look like that. So it depends on your perspective. Of course, there's not any true north or south or up or down in space. But for us on Earth, we say, well, downward to us is the Earth's core. And that's how we define downward. So we could, generally we just say that it's going to the ground, or negative means downward too. And so we could say the force is negative, or we can say downward. And then what is the force of the ball on the Earth? And this is the force of the ball, sorry, this is the force of Earth on the ball. And what is the force of the ball on the Earth? That's right, we just say upward, right? So we would say that the force of the ball on the Earth is the same magnitude. It's also 1.8, just in different directions. So the force of the ball on Earth is an upward force of 1.8 newtons. So we can say 1.8 newtons, we can say 1.8 upward, or positive 1.8. Those all mean the same thing. But we need to include direction when we talk about force. Any questions about that? Okay, the last thing to do for this one is to find out the acceleration of the Earth on the ball. Okay, so we talked about how the ball accelerates downward with this speed. So if you drop the ball down to the ground, the acceleration is 9.8. But what about the Earth accelerating upward? So the ball does pull the Earth upward. What is the acceleration of the Earth on the ball? So we would use F equals m times a to find the acceleration of the Earth on the ball. We know that the force is 1.8, but we need the mass of the Earth now. So before we looked at the mass of the ball and its acceleration downward, now we want the mass of the Earth, which I think was given to you in your book. Yeah, on page 104, they give that to you. Earth's mass is 6 times 10 to the positive 24th kilograms. And we can solve for the acceleration that the Earth experiences when the ball is above it. So divide both sides by the mass. Now I'll give you acceleration. Did you get that, Robert, or are you still calculating that? Yeah, it's gonna be very small. Not quite. Are you using the E button on your calculator? Huh. No, it's a double E button. It's the one that, yeah, use that one, because if you don't, you might get a wrong answer for that one. That one. Yeah, you don't have to memorize that. Don't worry. Yeah, I'll always give that to you. That's good. Yes. 3 times 10 to the negative 25 meters per second squared. That's pretty much nothing. I mean, it's such a small number. That's pretty, I mean, we're not aware of that, right? I mean, we don't feel the Earth. We don't see the Earth moving upward. So the acceleration is so slight, it's pretty much zero. But there is some acceleration. We can measure, we can calculate that. We just aren't aware of it because it's so small. All right, on page 104, work on those questions 28 through 31 for class today. Oh, it's on page 104, 28 through 31.